In this lecture, we will apply ray diagrams to a combination of lenses, and we will define refractive power of lenses, and from there on we'll look into light guides, and then we'll discuss about prism. This is a combination of two lenses, one a positive lens and the other a negative or concave lens. And a real object is placed here. First, you must have the optical axis, and then you define the focal length of the lenses. And this is f2. Then you draw the first ray from the real object that is parallel to the optical axis. And after passing through the lens, it will then pass through the focal point 1. To locate the image, you need at least two rays. So the second ray will be the ray from the tip of the object passing through the center of the lens, and they meet here. So this is where we locate the image. There is also a third ray that you can use, which is the one that passes through the focal point here, meets the lens, and after passing through the lens, it will be parallel to the optic axis. And all these three rays will intersect at this point here where we locate the image. In this case, it's a real image. So we will draw the ray diagrams for the lenses one by one. Now, this image becomes the object for the second lens, and is a real object for lens 2. So next, we will draw the rays from object 2 to the concave lens. The first ray is parallel to the optical axis, and then you align it to the focal point. Because this is a negative lens, so we'll align that ray to the focal point on the left of the concave lens, and then after passing through the lens, it will diverge. The second ray will be the ray that passes through the center of the lens, undeviated. The intersection between this and this is where we locate the image. Let's do the third ray. The third ray will be aligned to the focal point on the right side of this concave lens. After passing through the lens, it will then travel parallel to the optical axis. Projecting it backwards, it will also meet at this point, and hence we have the final image here. And in this case, this image is virtual because it's on the left side of this concave lens. This is an example of the ray diagrams drawn to show the formation of a final real image by a train of two convex lenses. And the overall magnification of the final image will be the magnification of the first image multiplied by the magnification of the second image. This table summarizes the thin lens formula as well as the mirror equation. This is for your reference. Next, we would like to define the refractive power of thin lens. This is the thin lens equation. We have reciprocal of the object distance added to the reciprocal of the image distance, and that will give us the reciprocal of the focal length. These reciprocal magnitudes are called vergence or curvature, and they describe the curvature of wavefronts incident on the lens, which is centered at O and I. Hence, we can represent the thin lens equation as P equals to V plus V prime, where V and V prime are the vergences of the object distance and the image distance. And P will be the refractive power of this lens and is the reciprocal of the focal length. The power is given in the unit of diopters, of which the focal length must be in the unit of meters. For example, for a lens with focal length of 20 cm, that would be 0.2 meters, and its refractive power would be the reciprocal of 0.2, and that would give us 5 diopter. If we have a few thin lenses which are stacked back to back, then the effective power of the entire combination would be equal to just a simple summation of the refractive power of the individual lenses. And here is an equation for thin lens, but it is given using distances referenced to another plane. And this equation is called Newtonian equation. Instead of referencing as object distance and image distance here, we will now reference it to the focal point. So we will have x distance and x prime. And you'll find that x multiplied by x prime will be equal to the square of the focal length. Here we will compare the spherical lens and the cylindrical lens. For the spherical lens, we have this beam that's incident on the lens will then be brought to a point focus, and it has rotational symmetry about the optical axis. This will provide symmetric focusing properties. We can say that the spherical lens is stigmatic. In the case of cylindrical lens, then these rays that are incident onto the cylindrical lens will then be brought to a line focus instead of a point. It does not have rotational symmetry about the optical axis, which would be along the plane here. And with that, its focusing properties will not be symmetric, and this cylindrical lens is said to be astigmatic. For this cylindrical lens, we draw a pair of rays along the plane that cuts the center plane of this cylindrical lens. We consider ray 1, which is from O to C to A, and another ray 2 from O to B. If you view from the top, you will see these rays here, where this stands for the cylindrical lens, and this would be ray 1, and this would be ray 2. Next, we consider ray 3 that would be incident onto the lens at the upper extreme, and this ray will be brought to focus to meet A here. And we take the fourth ray from O to the bottom extreme of the cylindrical lens, and this ray will be brought to focus at B. So if we view from the side, we will see that ray 3 and ray 4 will be brought to focus here. So the vertical plane has focusing property, whereas the horizontal plane is non-focusing. So from geometry, this is the horizontal plane, and this is the vertical plane. Position I here belongs to this line here. So if we view from the side, we will see them as just one point. So incorporating this horizontal and this vertical plane, we then can get the ratio of AB divided by CL equal to S plus S prime divided by S by consideration of similar triangles. So in other words, AB would then be equals to S plus S prime over S multiplied by CL. S, as you can see here, is the object distance, and S prime would be related to the image distance. This is a cylindrical lens. Line image becomes sharper when the candle flame is stable. The magnifying glass is a spherical lens. Every point of the flame is focused onto the image plane. To guide a ray from one point to another point, these are some of the light guides arrangement that can be used. Firstly, lenses can be used to guide light, as you can see from this diagram here. However, these refractive elements are usually partially reflective, and this will incur loss of optical power. Secondly, we can use mirrors to guide light, as you can see over here. However, mirrors incur loss of optical power too, because they are partially absorptive. A better way to guide the light ray would be utilizing total internal reflection. For this, we'll need an optical fiber. In this case, there is no refraction. Relatively, there is low optical power loss if special materials are used. Here is an example of an optical fiber. It has a core of refractive index N1 and a cladding of refractive index N2. In order to ensure total internal reflection, then N2 must be smaller than N1. Light rays that travel in the core are totally internally reflected from the interface with the cladding. When the incidence angle at the dielectric interface here is larger than the critical angle, which is given by the arc sine of N2 divided by N1. So from this diagram here, this theta would then be 90 degrees minus theta bar. Rays would then be confined in the fiber core if theta is smaller than the complementary angle of the critical angle. And that's given as 90 degree minus theta c. Here it will be given by the arc cosine of N2 over N1. The angle of acceptance of an optical fiber is defined over here. That would be the angle that defines the cone of light entering the fiber that will be propagated to the other end of the fiber. Applying Snell's law at this interface here, we have N0 sine theta A equals to N1 sine theta C bar. Theta C bar is equals to 90 minus theta C. So therefore, this will be written as N1 cosine theta C. And the numerical aperture of an optical fiber is defined as N0 sine theta A. Hence, it will be equals to N1 cos theta C. Now, cos theta C can be rewritten as root of 1 minus sine squared theta C. And at critical angle, sine theta C is given by the ratio of N2 divided by N1. Therefore, substituting this value into sine theta C here, we have the numerical aperture equals to N1 root of 1 minus the ratio N2 over N1 squared. And that would be equals to the root of N1 squared minus N2 squared. If N0 is 1, as in air, then the numerical aperture would just be the sine of the acceptance angle, or you can also express it as root of N1 squared minus N2 squared. Let's look at prisms. Prism can act as a beam splitter, a polarizing device, or an interferometer, but most applications make use of two main functions, which are, firstly, as a dispersive device, so it will separate the constituent frequency components in polychromatic light. Secondly, to make a change in orientation of an image or in the direction of propagation of a beam. In a dispersing prism, the refractive index and the speed of light would vary with wavelength. For the prism, as drawn here, with an apex angle of alpha, we have an incident beam making an incident angle theta 1, gets refracted in the prism, and then it exits, being deviated from the original direction of the incident beam. So the total deviated angle delta here would be given by the incident angle theta 1 minus the apex angle alpha plus arc sine of the root of n squared, which is the refractive index of the prism material, minus sine squared theta 1 multiplied by sine alpha minus sine theta 1 cosine alpha. Next, we will then derive this equation. With reference to this prism diagram here, the exit ray will be deflected by an angular deviation of delta given by the sum of delta 1 and delta 2, where delta 1 is the deviated angle of the refracted ray in the prism to the incident beam. We take the incident angle to be theta 1 and the refracted angle at surface 1 at point B here as theta 1 prime. And then this refracted ray in the prism would be incident at point D at an angle theta 2, and it gets transmitted out with a refracted angle of theta 2 prime. Looking at these two lines here, delta 1 would be equal to theta 1 minus theta 1 prime, which is here. And delta 2, we will look at these two lines here, will be equals to theta 2 prime minus theta 2, which is given here. We regroup this as theta 1 plus theta 2 prime minus theta 1 prime and theta 2. Let's check this polygon out. A, B, C, D. This is a right angle. This is a right angle. Hence, this angle alpha and this angle BCD should add up to be 180 degrees. Hence, the angle BCE would then be alpha, which is an exterior angle to the triangle BCD. Hence, alpha would be equal to the sum of the opposite two angles, which would be theta 1 prime plus theta 2. Then we substitute this expression with alpha, that will give us delta equals to theta 1 plus theta 2 prime minus alpha. And now we apply Snell's law to the second surface. Hence, we will have n sine theta 2 equals to NA sine theta 2 prime. Well, NA equals to 1 because this prism will be immersed in air. So we have theta 2 prime equals to arc sine of n sine theta 2, since NA is 1. And theta 2 is given as alpha minus theta 1 prime. Is the sine of the difference of two angles. Hence, it can be written as sine alpha cos theta 1 prime minus cos alpha sine theta 1 prime. So we use trigonometric identity, whereby we have cosine theta 1 prime being written as the root of 1 minus sine squared theta 1 prime. And we also have Snell's law being applicable at surface 1 at point B here.
That will give us sine theta 1, because NA is 1, equal to N
Sine theta 1 prime.
So sine theta 1 prime can be substituted as sine theta 1 divided by N. Since it's a squared term, so this term is squared. So we go back to this expression here. That would be arc sine of, inside the bracket, and sine alpha multiplied by root of 1 minus sine squared theta 1 divided by N squared, minus cosine alpha, and here we have sine theta 1 divided by N. Therefore, delta would then be theta 1 minus alpha plus this arc sine expression, which represents theta 2 prime. So from that expression, you can see here that if N were to increase, then this value in this bracket here would increase. In other words, the arc sine of this increased value would increase, and hence delta, the deviated angle, will increase. Since N is a function of lambda, therefore delta would also be dependent on lambda. In most glass materials, the refractive index decreases when the wavelength increases. Therefore, the deviated angle would decrease when wavelength increases. This will tell us that when lambda is longer, for example, red light, the deviated angle will be smaller. If lambda is violet, the deviated angle would be larger. As you can see over here, when we apply an incident white ray to the prism, it will be refracted at different angles for different color components, and as they exit, red gets deviated less, violet gets deviated more. Dispersion here tells us that the refractive index is dependent on lambda. If we use a monochromatic light ray at a fixed lambda, and this ray is incident on a prism with refractive index N and apex angle constant at alpha, initially starting at a small incident angle, as we increase the incident angle, the deviated angle would decrease up to a minimum. And this, we will call it the minimum deviation angle. After which, as the incident angle is increased further, the deviated angle will start to increase instead. At minimum deviation condition here, the ray actually traverses the prism symmetrically. That is, the ray through the prism is now parallel to the base of the prism. And from here, we can find that the refractive index can be given as the ratio of the sine of the minimum deviation angle plus the apex angle divided by 2 over sine half of the apex angle. So let's look at the derivation. From the earlier derivation of the deviated angle, we had this expression delta equals to theta 1 plus theta 2 prime minus alpha. Since at the condition of angle of minimum deviation, the ray traverses through the prism symmetrically, which means that this refracted ray in the prism will be parallel to the base, then theta 2 prime here would then be equal to theta 1. So we then replace theta 2 prime with theta 1, and that will give us theta 1 equal to del m, which is the angle of minimum deviation, plus alpha divided by 2. And from alpha equals to theta 1 prime plus theta 2, since there is symmetry, theta 2 would be equals to theta 1 prime. So therefore, theta 1 prime would then be equal to alpha divided by 2. So applying Snell's law at the first surface here, we have sine theta 1 equals to n sine theta 1 prime. N would be equals to sine theta 1 divided by sine theta 1 prime. And substituting these angle values into here, we have sine of half of the sum of the angle of minimum deviation and apex angle divided by sine of half of the apex angle. This equation forms the basis of one of the most accurate techniques for determining the refractive index of a transparent material.
After going through this lecture, you should be able to apply ray diagrams to arrangements of a combination of lenses. You should be able to differentiate between spherical and cylindrical lenses. You would be able to describe simple light guide arrangements, as well as derive the equation for minimum deviation in Prism. Thanks for watching.